Anim, Bojo, Sarah Hazel Dijnikaz, Nabising Donjaba. Hello and welcome. My name is Sarah Hazel and I'm from Nipissing First Nation. Thank you for joining me for this module on area mapping and spatial data management. Gathering, storing, processing, modeling, analyzing, and delivering spatial data is known as geomatics, and it is essential for unmarked graves investigations. Spatial data is information that is collected during investigations and associated with a specific location. For example, survivors might remember seeing graves at a specific location, or archival documents might indicate areas on IRS grounds that were used for burials. All spatial information collected needs to be organized in an appropriate spatial data management system. The ideal platform for this is Geographic Information System software. There are a wide variety of GIS software packages to choose from. Two of the most common are ArcGIS by Esri, which has become the standard software in many industries, but it comes at a high annual subscription. The other is QGIS, which is a free open source alternative that has become popular in the archaeological community and other organizations with limited budgets. While some larger communities may already have individuals experienced in GIS in their governments who can assist, given the central role that a GIS platform will have in your investigations, communities may wish to obtain funding to hire a professional GIS technician to manage the spatial data. One extremely important consideration when choosing your GIS platform is data security and its capacity for sharing. Much will depend on the product you choose and whether you opt for a cloud-based server and data storage or house the data on your own system. It will be important to use a system or platform that will also facilitate and support your research and investigation archives. With the recent appointment of the National Advisory Committee, more technical information should be available in the coming months to support communities on this critical issue. Once you have identified the areas you wish to search, one of the first tasks will be to create maps of those areas to help plan and organize your investigation. This will include identifying and mapping areas of high potential, mapping obstacles and other landscape features within and around the survey area, and laying out the grids required for geophysical survey. There are many mapping tools available depending on the location of the work. These include tape measures, total stations, global navigation satellite systems, global positioning systems, and drones. Prices range from $40,000 for a highly accurate GPS system to a $200 handheld GPS unit, or even less for tape measures. Regardless of which technique you use, the most important thing to remember in any mapping project is that it is accurate enough that someone else can relocate features and locations that you map on a future occasion. Ideally, communities should use tools that offer the greatest precision available to them and their budget. If you wish to have a very accurate map of your area, it might be cheaper to hire a surveying firm to come and do the work rather than buying the equipment yourself. If a GNSS unit or total station are not available, more basic methods can be employed. Tape measures, magnetic compasses, and simple theodolites, an instrument that measures angles, have been used for centuries for surveying. While they are slower and require some math, if used correctly, they are extremely accurate and come at a fraction of the cost. Using tapes and other non-digital devices requires the use of triangulation to determine the location of features. In triangulation, the location of a point is determined by measuring the distance, and sometimes angles, between the unknown point and several permanent landmarks in the survey area, such as the corner of a building or utility pole, that are also visible on satellite imagery. These measurements are then replicated on the satellite image within the GIS software to calculate the true geographic position of the point. If using this system, it is important to measure these points in relationship to enduring landmarks in order that the survey points can be relocated again in the future. Using hand tapes is slower and requires thorough note-taking to avoid replicability issues. They may, however, be the only option in some areas, such as woodlots, as tree canopy can block GPS signals and dense undergrowth can inhibit total station survey. A total station is a digital survey tool where the distance, angle, and height of a target are measured from a point on the ground where the geographic coordinates are already precisely known. Used correctly, a total station can have precision of less than 1 centimeter. However, a total station cannot detect where it is on the Earth's surface unless the total station unit also has an integrated GNSS antenna. Otherwise, a datum or point on Earth that has a fixed location, like the corner of a building, and can be viewed in satellite imagery will provide longitude and latitude coordinates. These coordinates can be used to calculate the exact location of the total station. The main advantage of a total station is its excellent accuracy, which is usually less than 1 centimeter. They also work well in and around buildings and trees, though areas with many obstacles that obscure the line of sight can be tricky to survey. They are considerably less expensive than a GNSS system, costing around $10,000 for an adequate unit, although prices can vary upwards for more fully automated systems. There is also a healthy second-hand market for total stations as engineering companies look to upgrade their systems to GNSS. The basic components of a total station include a theodolite, which is a precision optical instrument for measuring angles, and usually a stadia rod with a reflector or prism, although some more expensive total stations are reflectorless. The total station is set up over a known point on the Earth called a datum. This is ideally located near the area to be mapped. If a known datum is not available, a GNSS system can be used to create one. The total station is leveled and the geographic location, height of the instrument above the datum, and the bearing, which is measured in degrees, minutes, and seconds, to a second known point, called a backsite, is entered into the total station's computer. During a survey, one surveyor holds a reflector directly over the points of interest, while a second surveyor points the total station directly at the reflector using the telescope on the theodolite. The horizontal and vertical angles and the distance between the reflector and the theodolite are recorded, allowing the total station to calculate the location of the roving stadia rod relative to the known position of the total station. GNSS is the generic term for groups or constellations of satellites that send position data to receivers on Earth. The Global Positioning System, or GPS, is just one of many constellations that is commonly used in North America. Most high-precision surveying systems on the market today take advantage of accessing multiple constellations, including GPS, and are thus known as GNSS systems. GNSS is generally considered the gold standard for surveying and often provide the ideal solution for accurate and precise global positioning wherever conditions allow. These units consist of at least one and sometimes two antennas that receive information from satellite networks and generate coordinate information that is globally accurate to less than 2 centimeters global accuracy. This means the error between the collected point and its actual global position is less than 2 centimeters. GNSS systems are used with data collectors, small handheld computers, allowing the automatic recording and description of survey points. This saves considerable time during a survey. Many models come with a base and a rover, like pictured in this image, whereby the base is placed in a single known location and the rover collects points over the survey area. These are known as RTK, real-time kinematic systems, where the stationary base transmits information to the rover by radio signal to help refine the precision and accuracy of the coordinates determined by the rover unit. Specific setups vary depending on the manufacturer, but the basic process is generally the same. The base station is placed in an area with minimal obstructions, away from buildings, trees, and other objects that might interfere with satellite signals, and left to collect data for a set amount of time, typically a minimum of 1 hour. A radio transmitter, either built in or separately attached, is set to a frequency to broadcast corrections. A rover unit is then set to the same frequency and attached to a pole or placed in a backpack. Locations requiring precise and accurate spatial data are mapped using the rover. In surveys for unmarked graves, map locations may include the corners of grids established to collect information using various geophysics instruments, such as ground-penetrating radar, or may include control points to correct the georeferencing of drone imagery. Once mapping is complete, the information from the base station can be sent for post-processing. In Canada, this typically involves sending the files from the base station to National Resources Canada, which then returns the corrected coordinate for the base station. The major limitation of GNSS units is that they only work where there is adequate satellite signal. Areas near buildings or with many trees or other dense vegetation can be troublesome. Any obstructions blocking the satellite signal can mean a significant loss of precision and in some instances will not work at all. Cost is another major factor. High precision RTK base and rover systems start at around $30,000 and can be as expensive as $60,000. The proprietary software they operate also needs to be purchased and renewed annually, increasing the overall costs. Unmanned aerial vehicles, or drones, have different levels of accuracy depending on what system you use. Most enable the mapping of features to within plus or minus 1 meter of their global position and can be purchased for under $1,000. Their main advantage is that large areas can be surveyed very quickly and relatively easily. However, the level of accuracy offered by many drones might make it difficult to relocate features of interest precisely in further investigations. Using ground control points can improve accuracy of drone surveys, though these require an additional survey instrument such as a theodolite or a GNSS system to locate their positions. When searching for unmarked graves around residential schools, a few different things should be mapped. These include, but are not limited to, survey grids set up for the purposes of near-surface geophysics such as GPR. Corners of the grids should be mapped, and where grids occur on a significant slope, points within the grids should also be documented to correct the elevation of the collected geophysical data. Control points for imagery collected from drones. Drone imagery is more precise when control points are mapped. Typically, highly visible targets are placed on the ground and mapped using a GNSS system. These targets are then used to correctly place the imagery on the Earth's surface in a GIS system. Other landscape features of interest. The most common would be the positions of grave markers, building foundations, fences, or the locations of graves visible on the surface through depressions or mounds. All landmark features used as reference points during a triangulation survey should also be mapped. Miigwech. Thank you for joining me for this module on area mapping and spatial data management. Please take care.